the former president of University of Geneva, Maurice Bourquin. We have also a very large contribution from Taiwan, and this contribution is mostly in electronics. We have 650 microprocessors, and most of them are made there. And this is done by Professor Lee, who, again, recently been selected to be member of the Academy of Academic Sinica. So after my presentation, after your question, and you please reserve hard questions to my colleagues. And so people ask you, you have spent close to $2 billion. What are you doing? What are you going to learn? The issue of antimatter in the universe and the origin of dark matter, of course, probes the foundations of modern physics. But to a scientist, the most exciting objective of AMS is to probe the unknown, to search for phenomena which exist in nature that we have not yet imagined nor have the tool to discover. So let me share with you the major discovery in physics over the last half a century. When I first received my doctorate degree, there were two largest accelerators, one in Geneva, one in Brookhaven. The original purpose, the review from members of the National Academy of Science by leading scholars to say these accelerators are very important, you can understand nuclear force. What was discovered was something called neutral current. There are two kinds of neutrinos, breakdown of time reversal symmetry, and new form of matter. Most of these were given Nobel Prizes. United States in 1970 built a 400 billion electron volt Fermi National Laboratory to study neutrino physics, and what was discovered was the fifth type of quark and the sixth type of quark. The Stanford Linear Accelerator in 1970s was to understand the property of electricity. What was discovered are partons, the fourth type of quark, and third kind of electron. The large underground cave in Japan, its original purpose was to look at how long protons live. What was discovered was neutrinos actually has mass. Even Hubble telescope, its original purpose was galactic survey. Among its many discoveries are the flat curvature of the universe and the existence of dark energy. And so for AMS, facing all of you, I have mentioned we can look for dark matter, look for antimatter, look for strangelets. We say this because this is our current knowledge. But advance of physics is to push the current knowledge aside. Then you can move ahead. And so exploring new territory with precision instrument is the key to discovery. What we really would see, nobody knows. I mean, if you find what you predicted, it's not interesting. The interesting thing is to destroy the current idea, to find something new. This is how science advances. So I've finished now, and I'm happy to take questions.
Thank you, Professor Ting. The AMS collaborators that Professor Ting identified will be available at the conclusion of this briefing for your questions. For now, we'd like to limit your questions to those who are on our panel. Please wait for the microphone, state your name and affiliation, and to whom you're addressing questions. We'll start over here with Seth Bornstein.
I'm sorry, Seth Bornstein, Associated Press. For Dr. Ting, In terms of the antimatter search, I know you have an expected 20-year lifetime. First, in that 20-year lifetime, if the space station's lifetime is just, it may not have been made 20 years itself, but if you don't find anything in that 20 years, would you therefore conclude that maybe some of the theories are wrong, or is it just that you haven't had enough time? And then as another part of that, given what we know, how long, if current theories are right, how long would it take, do you expect to take to detect antimatter?
I'm an experimental physicist. Before I become an experimental physicist, I actually did some theory. So let me answer you in the following way. Because it's so difficult to put a magnet in space, the magnet in space will always rotate. And so if you're not careful, your space shuttle, space station will lose control. Our first flight proved you can actually put a magnet in space. Now, with such a large magnet, with such a precision instrument, if at the age of observable universe, if there are equal amount of antimatter, there will be order 10 to 20 arriving on the in AMS. If you expect 10 or 20 anti-helium or anti-carbon, and if you didn't see one, something is wrong. And the interpretation is difficult to say. Okay. Because the reason antimatter, we do not see antimatter, has never been found. There are many theories and predict many results, but none of them has been correct. Have I answered you?
Is there a time you would expect, if you're seeing 10, 20 antiheliums, in other words, as a science writer, how soon should I expect you guys to be up here or at headquarters saying we found something?
Oh, I have advised my colleagues. Right? It took us many years to build this thing, right? And there are multi-redundancies. By any standard, it's an extremely precise, accurate detector, and we have calibrated detector over again in test beam, in accelerators. And so we are going to do this very slowly. Carefully check everything. And we're going to form 2 analysis groups to check each other. And so we're not going to publish preliminary results and confuse everyone. So we're going to do it very, very carefully. Fortunately for us, perhaps we don't have any competition. So we're going to do it carefully on our own, and but do it right. So I'm not able to tell you how long it will be.
In the front row here.
Jim Siegel, Celebration Independent Newspaper. I have a two-part question for Mr. Gonzalez. First of all, I'm curious as to why the Department of Energy is involved in this project, in fact, leading it, as opposed to some other agency of the United States government or some other entity. And secondly, given what Professor Ting told us a couple of weeks ago during a briefing about the amount of energy that is potentially contained in cosmic rays, whether you would expect it possible that a discovery from the AMS may result in some significant find that would help the energy supply of the United States or of the world.
So the second one I'll take first. And I think as a scientist, I would say never. But the details I will leave for Professor Ting to answer. And the first one, why DOE? We have an Office of Science within DOE, And that office is the single largest funding agency for physical sciences in the U.S. and has a broad portfolio, and part of it is fundamental research, which is where high energy physics, the office I'm in, falls into. And this AMS, what it does, the goals of AMS, that science mission, just falls perfectly with what we do. We have a number of national labs in the U.S. that are trying to address the same question in different ways, and using accelerators. And we fund research at the LHC at CERN, for example, which also tries to address this question. So I think the answer is that's what we do.
Okay, we'll take a couple of questions on this side of the room before we come back over here.
Mark Boucher, Space Ref for Professor Ting. Can you characterize the differences and capabilities between AMS, which flew on STS-91, and AMS-2?
Oh, first of all, AMS-1 flew for 10 days. AMS-02 will last the duration of space station. That's number one. Number two, AMS-1 has four type of detector, and AMS-2 has 7 very precise detector. The size and scope and the precision are totally different. In AMS-1, we just do the proof of principle. In AMS-2, what we have decided to do is to do as precise, as accurate as we can manage it. We try to push the envelope to the limit.
My question's for Dr. Ting. My name's Randy Att with Sky News Magazine. Just a follow-on to the previous question. Were there any lessons learned during the first AMS flight that changed your thoughts on the design for AMS-2?
No, sir. AMS-01 just showed everything worked. We published a few papers, extremely interesting papers, and nothing learned, just except everything worked.
Back over on the other side of the room.
Hi, I'm Alan Boyle with MSNBC. For Dr. Ting, before the startup of the LHC, there was a lot of talk about strange phenomena that might happen, creation of black holes, creation of strangelets. Do you think that the AMS experiment will shed light on those nightmares that people used to have? Because a lot of physicists said at that time, well, if these phenomena occurred, they would be occurring out in space, and we would have cosmic signs of that. What sort of cosmic signs do you think AMS would produce, either to kind of still any sorts of worries about nightmares or shed more light on strangelet phenomena?
I do not know how to answer these philosophical questions. Our only nightmare for AMS during the 17 years was to be removed from the manifest. That was indeed a nightmare. But to the credit of DOE, to the credit of NASA, to the credit of my senior collaborators from different countries, everybody realized this is such an important experiment. Even when we were off the manifest, nobody stopped us. Nobody stopped funding us. We still continue. That's the only nightmare I had.
Go ahead.
This is Mark Ratterman from Talking Space. Professor Ting, I bring you a question from a science advisor for our show, Catherine Qualtrough, and her question is about some recent events. The RHIC, the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, has recently reported the first ever observation of the antimatter helium nucleus, antihelium as you've called it. Can you address the importance of this find and how it relates to the goals of AMS?
They are not related at all. Right? Anti-helium, right? The helium is 2 protons, 2 neutrons. Right? And it has an isotope called helium-3, 2 protons, 1 neutron. Both has been observed, but should have been observed. Right? The question is, the hidden question, an important question you ask is, could nuclear collision in space produce this? Okay. And the rate, what they observe, is so low in space from cosmic ray collision will not produce this. That's number one. Number two, if we see anti-helium, we should also see anti-carbon and other nuclei. And these cannot be produced by accelerators on the ground because the mass is so large. So it's interesting, right? But really had nothing to do with us.
Ken Kramer.
Hi, Ken Kramer for Spaceflight Magazine. Professor Ting, as a scientist, you're probably thinking maybe a little bit about the next experiment. What would you like to do beyond this? Thank you.
I think probably Professor Scher, Professor Battistone, and academician Lee can answer these questions. And for me, if you look my career history, I have always do one experiment at a time, because I always view my ability is limited. Okay, we have just started, as Mark just pointed out. Okay, this is the first step. This experiment will last 10 to 20 years. And so probably it's a little bit too early for me to think about the next experiment. But there are different kind of people. Many people are much more gifted than me. They can do 4 or 5 things at the same time. And I'm very limited. Only one thing very slowly after another. But I don't let it go. I want to understand everything.
Clara.
Clara Moskowitz with Space.com, and this is a question for each of the participants. If you could just address what you felt when the experiment was taken off the manifest, and if you had personally given up hope that it would ever get to fly.
You're asking who?
Let's start with you.
Ask me. I was very surprised. I was very surprised, but to the credit of people in NASA headquarters, okay, in Johnson Space Center, even who were off the manifest, the key support from the Mission Management Office continue to support us. And the Department of Energy has a thorough review of some of the best scientists in the United States. And they advised DOE, this is such an important thing, we should carry on. Okay? And similarly, the French, the German, the Italian, the Swiss, the Taiwanese, the Spanish, all decided to carry it on, even though whom had no flight. You have to understand, I have no financial authority over any of my senior colleagues. People join this because they found the physics is compelling. And that's why we managed to finish. So I would say surprised is the most polite word I can think of.
I think from the DOE perspective, clearly we never gave up hope, and just because the science was so compelling, and that's what we focused on keeping the experiment going, the collaboration going, and yeah, we certainly didn't give a hope. We were very concerned at times, but things worked out. So we're just very happy to be here today.
Well, on behalf of NASA, I would have to share both Sam's and Saul's comments. I think the flip side of that coin, to answer your question, it's important to also note who was responsible for helping us get our flight back. And unfortunately, not present here today is William Gerstenmaier, the Associate Administrator at NASA for all human spaceflight. Certainly among us, I would have to say that we owe a tremendous amount of debt to Bill Gerstenmaier, okay, because it was his leadership, okay, through those hard times that eventually won us back our shuttle flight, okay. And without Bill Gerstenmaier, we would not be here today. I think that's all I want to say about that one.
In the back.
Matthias Grunder from German aerospace magazine Flugrevue. Professor Ting, do you expect some technological upgrades of the instrument over the lifetime, for example, like the Hubble Space Telescope?
Hubble telescope shows the importance of human flight. It's upgraded 6 times. For us, we don't have this luxury. The space shuttle will terminate soon. And we have tested the detector on each component level, on detector level, in accelerators, and in thermal vacuum conditions. And then we test the whole thing at CERN with different beams. And we have most of the major electronics, 400% redundancy. Hopefully, we do not need any upgrades. There's no way to upgrade it. We have checked the magnet. The magnet first was used in '98, and recently in Aachen, we measured again, and the magnetic field still have not changed within 1% over 12 years. The consumables we have can last, we have measured it, and last more than 30 years. Without a shuttle, you are not going to think of an upgrade.
Go ahead.
Jim Siegel, Celebration Independent newspaper again. Professor Ting, at what point after launch does AMS start operating? Do the crew members actuate it to begin that process? And do the crew members on the ISS have anything to do with collecting or analyzing the data or sending it back to Earth, or is it all automatic, or what?
First of all, on the 4th day, we will be moved from the shuttle bay to the station, and then we will be connected to the station. And then within a few hours, we should be able to get our events. And this is such a complicated detector. And we do not think it's a good idea to waste the astronauts' time. Okay, because you really have to be 100% dedicated to such experiment. Okay, so we have not dared to bother them.
So it will happen by itself. You will turn it on from...
Yeah, we will do all the control ourselves.
Go ahead.
Professor Ting, Angela Swafford from Muy Interesante magazine. Can you compare, or would you compare, the AMS mission with the WMAP mission, which were, I think, probably the 2 biggest missions in terms of the fundamental questions? Are they comparable, and can you?
I do not know how to compare this. The WMAP founder, Dennis Wilkinson, who who passed away was my good friend at University of Michigan. Also, I've known him for a long time. Took him many years to build the WMAP. Unfortunately, he passed away quite early. Besides that, they are doing great work. I would not know how to compare this.
Mark Ratterman again with Talking Space. On the AMS02.org website, I saw a mention of galactic cosmic rays being an obstacle to manned interplanetary flight. How will AMS help to find a solution to that problem?
I do not read websites. And my family, particularly my son and my daughter, and read some website about me, said, "No, Daddy, this is not you." So I don't look at websites and don't read them. It is important to know a charged particle changes trajectory in a magnetic field. This was discovered 100 years ago. If you carry a man to space, when you leave the protection of Earth's atmosphere, Earth's magnetic field, you expose yourself to intense radiation. So if you go to Moon and Mars, this radiation in 3 years will kill you. And therefore, there's no, unless you have a protection, there's no need to come back. Because it takes 3 years to get there. Using a magnet system, a superconducting magnet system, is, in my opinion, the most effective way to bend the charged particles away. This is used repeatedly in all the laboratories in Europe, in the United States. When you have radiation particles, you use a magnet to bend the trajectories. So the development of a magnet system is extremely important. Indeed, some of my collaborators, Professor Boddystone is one of them, has studied this.
Seth Bornstein again at AP. For Dr. Ting. So on the fourth day, you get moved to this from shuttle to station, and it automatically turns on. If you can go through the timeline of when you know that all the systems will be that are operating okay, how soon thereafter? 8 hours. And then when there's usually a shakeout period in scientific instruments, when do you start getting actual data? Or
when I say 8 hours, I mean 8 hours shakeout time.
That's all? It only takes 8 hours of checkout time?
We have taken this detector, even though it's a very complicated detector, we have disassembled, assembled, disassembled, assembled, disassembled, assembled 3 times. I dare say we are quite familiar with what's going on inside.
So just to follow up on that, you'll be getting data 8-9 hours after you've moved. Given you're looking for very difficult to find data, I mean, is there something you're searching for also that will be showing you we're getting something far easier to find than antiheliums? And so will we, I mean, in Houston on day 7 or 8, could I come to you and you could tell me, yeah, we're finding this so far, it's nothing new, but it's something that's showing...
You're welcome to visit us.
Would love to visit you.
Yeah, welcome to visit us. And we are building a very large park and SOC in Geneva. And we made basically a carbon copy interior of what's on the park and SOC in Houston because they look good on television. And I would say, for me, it will take quite some time before I open my mouth, say that we have found something.
Seth, on Flight Day 4, as part of the mission status briefing during the mission, Professor Ting and Mr. Sestili will be involved in the briefing with the flight directors to talk about the results that have been acquired. And we'll take a final question from this side of the room before we wrap up.
Scott Powers from the Orlando Sentinel. Dr. Ting, could you respond briefly to some of the critics out there, such as Professor Tarley at the University of Michigan, that have raised some strong concerns that you will not find either primordial antimatter or dark matter?
University of Michigan is where I went to school. Used to have a very good football team. In the last few years, their football team has gone to pot. Last year, they have changed the coach. I have no other answers.
All right. Thank you all very much. We'll wrap it up. I wanted to let you know that once again, at the conclusion of this briefing, you may ask some questions of the AMS collaborators here. Our next event on NASA television will be the rotating service structure retraction tonight, when Space Shuttle Endeavour is revealed in the lights, and that will be at 7 p.m. Tomorrow morning, managers will meet to discuss whether they should go forward and tank the external tank. They'll meet at 5:45 in the morning. Our coverage of fueling would begin at 6:15 a.m., and our continuous coverage of launch will begin at 10:30 a.m., leading to liftoff of Endeavour at 3:47 p.m. tomorrow. You can keep up with all of our activities on the web at www.nasa.gov.